Okay, I think we're going to get started. Hi, everyone. I'm Graham Maidman. I'm my day job is with the UK government, Department of Energy Security and Net Zero, but I'm here representing the International Institute of Refrigeration as Commission E2 President of Energy Recovery and Heat Pumps. And welcome to the first webinar of the IIR. So we're trailblazers. The first one is from this commission. So great to have 137 people on the call. And it's great if we can go to the next slide, please, also to have four fantastic speakers from a range of different backgrounds here. And we have Emilio, who's professor from UPV in Valencia. We have Daniel Colburn, who I've known for many, many years, who's an expert in hydrocarbons. We have Tor, research engineer from Fraunhofer, and we have Bourne Palm, senior professor from the KTH Royal Institute of Technology. So amazing speakers on a really important topic: domestic domestic heat pumps and hydrocarbons. So we've got 4 presentations. They're shown here. That's our agenda, and hopefully we've got 10 minutes for question and answers at the end. But we're going to use the chat as well. Feel free to use the chat and put questions into the chat, and we'll try and field these as we go along if we're able to, but we will use the 10 minutes at the end as well. So that's the agenda. Next slide, please. Just a big introduction. The IIR, International Institute of Refrigeration, was founded in 1908, so long time ago. And the core vision is here and core values here. Lots of member countries here, and it's about making sure that it's an intergovernmental organisation, and it's about collaboration and in a technical area. Sustainable refrigeration, heat pumps for all is the vision. Go to the next slide. Okay, we've got 5 IIR sections. We're part of E2, which is air conditioning, heat pumps and energy recovery, but we've got some others as well: storage and transport, biology and food technology, thermodynamics, equipment and systems, and cryogenics. And you can see here, this is the government structure, and you can see we've got the great and the good at the top, and we're at the bottom on the right hand side, energy recovery and heat pumps. And if you're interested in finding out more, I will put my email, or maybe one of the colleagues from the IR will put our email in, and we can add you to our list of documentation. Yeah, so our role of the IIR commissions, it's research and development. Firstly, identifying trends, challenging innovations in refrigeration. And that's really important in today's presentation. Standardization and regulations, and again, it's really important. Knowledge sharing, again, that's what we're doing today, and technical publications. So this webinar is to support a publication that was produced at the end of last year, November, by the team on the topic. So this is knowledge sharing of that technical publication.
Test.
Okay, go to the next slide, please. Okay, so just a bit of background. I guess we're all here because of this graph, the fact that we've got this trajectory of uptake of potentially of heat pumps being really significant in the future, and we need to be able to meet that in the very short term to deliver low carbon heating with our decarbonised electricity supply. If we go to the next slide, please. 600 million heat pumps. That's the headline from the IEA, and it's a recent headline. Okay, by required by 2030, covering 20% of our buildings. Next slide, please. And these are the sales of heat pumps. And final slide, please. I think. And this is the challenge. One of the challenges, we're used to using hydrofluorocarbons extensively in many applications, but we have a phase down. We have the EU F-gas phase down, and other countries have had their own phase down of the availability of these refrigerants. Our quotas of these refrigerants are going to mean that using these refrigerants, HFCs, are going to be tricky. So we have to use alternatives. And one of the best alternatives are hydrocarbons, but we need to use them sensibly, and you're going to find out more about how we're going to do this today. So that's the purpose, and I'm going to hand over to Emilio. He's going to start with 10 minutes on the advantages and challenges of hydrocarbons in domestic heat pumps. Over to you, Emilio, please.
Thank you, Graham. So now in this presentation, I will talk about advantages and challenges of hydrocarbons to be used as refrigerants in domestic heat pumps. I would say that nowadays the most common fluids used for these applications are R410A and R32, but this refrigerant has a high global warming potential, and for that reason, some countries has put some limitations to their use, and some alternative has to be seek. Among these alternatives, I would say that the most natural alternative is hydrocarbons, and also probably the most or one of the most suitable ones. We think in hydrocarbons because they are natural refrigerants, and by natural refrigerants I mean that they have been in the atmosphere for a very long period of time, and we know perfectly which are the effects of releasing this kind of fluids to the atmosphere. They also have a quite low global warming potential. In addition, they have very good thermodynamic properties, and in this talk I will go more in deep why we say that they have good thermodynamic properties, and particularly we perform an analysis dedicated to propane, which is a refrigerant that for this application we think that is quite suitable. And regarding the main challenges of hydrocarbons, we have to say that this family of fluids are flammable. And at the end of my presentation, I will comment some points about how to deal with that question. And also, I think that during the rest of the webinar, other speakers will talk also about that point. So, going to the more specific contents of this talk, just in order to evaluate why we say that propane, in this case, has very good thermodynamic properties, we have performed this, we want to show this analysis in which we have compared the properties or the performance of propane compared with other fluids that are that could be considered to work in this application. In order to do that, we have simulated a vapor compression cycle. In some typical conditions for the heat pump, we have assumed that we have a constant compressor efficiency of 80% for all the fluids that we are considering, and we have assumed that this vapor compression cycle will produce a heating capacity of 10 kilowatts. So based on that, in this table, we show the results that we have obtained for the different refrigerants. We can see that the heating COP for propane is the highest among the different fluids considered. It is true that the differences are not so high. I mean, if we compare propane with R410A or with R32, the difference is around 3-4%, but it is better. Also, if we compare the pressure ratios for each refrigerant, we also can see that the propane has the lowest pressure ratios among the different fluids that we have considered. This value probably has associated that when we go to a real cycle, the compressor efficiency that in this case we have assumed that is constant for all the refrigerants will be better for propane as a consequence of working at lower pressure ratios. Then if we go to the swept volume of the compressor, or I would say the size of the compressor, in this case we can see that if we compare the size of a compressor working with propane and the size of a compressor working with R32 or with R410A, we need to increase quite a lot the size of the compressor for propane in order to supply the same capacity. But if we compare propane with other alternatives to this refrigerant, like R1234YF or R454C, we see that in those cases the size of the compressor is not a disadvantage. In this context, I would like also to talk about the other, I would say, most important components of a heat pumps in terms of cost, which is the size of the heat exchangers. Now, in order to do that, I would like to show you this study that has been done by Daniel Corbun to GAC, in which he compared the size of the heat exchanger of air-to-water heat pumps and liquid-to-water heat pumps for different refrigerants, and he expressed these results in terms of the weight of the heat exchangers. The reason to explain the size or the volume of the heat exchanger in terms of weight is because usually the cost of the heat exchanger is proportional related with the weight that we have of that heat exchanger. And in those cases, we can see from this study that the size or the weight of the heat exchangers using propane is more or less, I would say, similar to the weight of a heat exchanger designed for a heat pump of R14A or for R32. So no increase of cost will be expected from the changing from the current refrigerants to propane. If we compare these results for R1234YF or even for R454C, the results shows that for two refrigerants we have to increase quite a lot. We have to increase in a significant way the weight of the heat exchanger. So now, continuing with this thermodynamic analysis, the last variable that I would like to show you is related with the discharge temperature. We talk also about the discharge temperature because in some way it's a degree of the operation map that we have with the heat pump or with the compressor. And here, when we compare the discharge temperatures, we can see that the discharge temperature for propane is also significantly lower to the discharge temperature that we have with R32 or with R14A. This means that it is not complicated to find in the market compressors working with propane that are able to have to work at the evaporating temperatures of -10 degrees, having condensing temperatures of 80 degrees without requiring any kind of liquid or vapor injection in order to operate on that on those conditions. Therefore, with propane, we can cover just with a single stage compressor all the typical operation map of a heat pump. Up to now, I have talked about the thermodynamic properties, or I made a comparison of the thermodynamic performance of propane compared with other refrigerants. Now, in this second part of the presentation, I would like to pass to talk about which is the real behavior of propane in the components of a heat pump. First of all, I would like to comment that you can find many studies in the literature in which a compressor is tested working with propane and working with other refrigerants. And usually the most common result is that when you operate the compressor working with propane, the compressor efficiency is higher than when this compressor operates with other refrigerants. Here you can see some figures in which we have represented this kind of tests in a comparison between propane and R22, propane and R1234YF, propane and R47C. And finally, going to also to real results, we have performed the following comparison. Taking results from the KMAR database from 2022, we have selected the heat pumps that are on this database, the heat pumps, air-to-water heat pumps and water-to-water heat pumps that you can find on this database working with propane, and the heat pumps that you can find in this database working with other refrigerants, and mainly those refrigerants are R32 and R14A, because as I told at the beginning, they are the most common refrigerants used for this application nowadays. And we have represented the COP of those heat pumps based on catalog data as a function of the nominal capacity. And you can see in both figures that heat pumps working with propane generally have a higher COP than the heat pumps working with the rest of the refrigerants. Related to that, it's also interesting to make a comment about the figure that I put here on the right side, in which I have represented the refrigerant charge as a function of the nominal capacity for those propane heat pumps. And you can see that for air-to-water heat pumps, you can obtain those values of COP with a specific charge of a little bit more than 50 grams per kilowatt. And if you go to water heat pumps, these COPs can be obtained with heat pumps that has a even lower specific charge of 20 grams per kilowatt. And this is something that nowadays is commercially available and is supplied in the catalogs of the heat pumps. So just to conclude my presentation, I would like to say that the use of hydrocarbons, and particularly as we have shown in this presentation, propane, are a good alternative to reduce the direct, but also the indirect emissions associated to heating and cooling in the domestic sector. And also the specific charge of the commercially available systems allow nowadays the introduction of air-to-water and liquid-to-water heat pumps working with propane in single-family houses. Then, regarding just a last comment about the flammability of this kind of refrigerants, I would say that from the engineering point of view, the most common approach since almost 100 years ago has been to use an approach based on chemical engineering, in which they have tried to avoid the flammability of these refrigerants, just engineering the hydrocarbon molecules, removing the hydrogen or making some kind of different chemical bonds among the different carbon molecules. This approach, during this almost 100 years of experience, has shown that although it solves the flammability, it has associated other problems to the environment that in many cases are even more difficult to solve than the flammability itself. So for that reason, I think that in the next talk, the next speaker will talk about other not so aggressive strategies to work with flammable refrigerants like propane or other hydrocarbon refrigerants in such a way that we can work with them in a safe way and in an environmentally friendly ambient politic.
Fantastic.
Okay.
Thanks very much, Emilio. That was tremendous. 10 minutes
Okay.
understanding the advantages and disadvantages of the refrigerant. Brilliant, absolutely brilliant. And it leads us really nicely into our next speaker. But before we go there, just if you can have a look at the chat, Emilio, there's a number of questions in terms of the refrigerant charge, in terms of capacity, etc., which you might want to answer. And can I encourage everyone to use the chat and to type your questions in there? There's some really good questions in there that that others are probably wanting to know as well. So there's no silly question. Please add whatever you can. I'm going to go to Daniel. Daniel's going to talk about safety and technological landscape. He's well known, Daniel, so I probably don't need to introduce much more than that. So I'll pass you over to you, Daniel.
Thank you very much, Graham. So good day. So following on from Emilio's remarks, it's important to first of all understand the let's say legislative framework when applying refrigerants or refrigeration systems. Importantly, at least within Europe, whenever you place a product on the market, it has to be safe, and that is defined by various regulations that that prescribe how certain hazards are to be addressed. And related to our fields, there is the Machinery Directive that I'm sure most of you are familiar with. There's the Pressure Equipment Directive, and there's various others as well. Below these regulations or directives, there are safety standards, of which some are harmonized. Harmonization means that they provide a presumption of conformity, or certain clauses provide a presumption of conformity to the requirements within the directives or regulations. So within the heat pump sector, there's a number of safety standards that prescribe those various requirements for ensuring the required level of safety associated with the various hazards. Then, in addition to the safety standards, there are various industry guidelines, and these guidelines aren't legal requirements, but they often take legal requirements and provide a more detailed interpretation of them. The most important, or one important point that I want to emphasize, is that whilst we're talking about hydrocarbons and which are flammable refrigerants, there are a whole load of other hazards associated with heat pump systems that also need to be addressed. I've got a list on here on the right hand side of the slide. So there's vibration, asphyxiation, hot surfaces, so on and so forth. And so it's important to just take a step back sometimes and recognize that it's not only flammability that's providing that hazard, but there's all sorts of others to bear in mind. So within those safety standards, increasingly there's various mitigation measures that are, let's say, provided or offered on the menu of measures that can be applied to systems with hydrocarbons that help to mitigate that flammability risk. So not all of them are mentioned here, and they're distributed across different standards, but just to mention a few, there is of course improved system tightness, which most of you would agree is of importance. There's what we call limited releasable charge, where you can use valves or other components to prevent a proportion of the refrigerant from leaking out of the system in the event of a leak. There you can apply room ventilation to extract a release of refrigerant, eliminate potential ignition sources. That's generally applicable to all cases. And there is the circulation airflow option, which enables a release to be dispersed almost homogeneously throughout the room. Natural ventilation, of course, particularly for heat pumps that are located outside. There are minimum separation distances to avoid access or gas flowing into parts of the building. There's a mechanically ventilated enclosure option, where the whole refrigeration system is inside the enclosure, and there is a extract ventilation to exhaust the leaked refrigerant to the outside. And then of course there's the limitation on refrigerant charge as well, which may be related to the room size, or it may be applied to an overall cap limit for systems. Related to this refrigerant quantity limit, this is perhaps the most, or one of the most contentious topics that we have to handle. The graph here, which I apologise for the complexity, but after staring at it for a while, it becomes clear, I hope. The graph shows the refrigerant charge on the y-axis and some nominal thermal capacity on the x-axis. The lines show the refrigerant quantity limits within the standard for air conditioners and heat pumps, this 60335-2-40. And these limits are related to room size or an overall cap that's irrespective of the room size. All the data points are for real systems. The green ones are for actual R290 systems, and the other coloured ones are HFC systems, but the system charge is adjusted according to the density of R290. So overall the graphs shows that at least for air-to-air systems, the vast majority of systems fall under the charge limits imposed by the standard, and for air-to-water or monoblock systems, water-to-water as well, most of those fall below the 5 kilogram limit as well. So it's just a general overview to illustrate that at least at the moment, the majority of systems can adhere to the requirements within the standards. There are, of course, exceptions to that. And then lastly, just a couple of words, not really detailed within the safety standards that I've mentioned, but just to highlight the importance of carrying out risk analysis or quantitative risk assessment. So within the safety standards, you have various requirements, and that's what I call safety standard safety. And then you have what you might consider to be real safety. So rather than assuming a very, very large leak hole, of course, in real systems, you have a variety of different leak holes. So it's important to consider all these different hole sizes, environmental conditions, and so on and so forth. But the advantage of doing this is that you can make a sensible balance between sort of the level of risk and the expenditure. So you may, for instance, you could invest a lot of resources into one element, but it may not be as cost effective in terms of risk reduction as applying to other elements. More importantly, it's very useful to look at the level of risk associated with, let's say, the flammability compared to, let's say, the background or the residual fire risk that are associated with heat pumps, air conditioners, fridges, and so forth. And what you can see in this graph on the, or this image on the right, the background fire risk, which is normally due to electrical faults, is significantly higher than the flammability fire risk. So this is an important factor to bear in mind when applying resources to the design of the equipment. So that's the last slide for me. Thank you very much for your attention.
Thanks very much, Daniel, and a wealth of information delivered really quickly in 8 minutes. So that's great. Gives us time for questions later on. Thanks very much, Daniel. And now we've got Tor Ottersdorf from the Fraunhofer Institute Solar Energy Systems, who's going to give us an update on the market. So over to you, Tor.
Yeah, thank you, Grammy. Yeah. When we started to write the informatory note, it was a difficulty to find data about the market, and by some incident we have some insight into the market development in Germany, because the German funding programs for heat pumps is somehow designed in a manner, or at least was designed in a manner until the end of 2023, that if you wanted to apply for a heat pump, you needed to give some information about the heat pump model you're going to buy for your house. In Germany, you have two different funding programs. That's the BEG and the BEW, in which heat pump funding takes place, and it's the basis for climate neutral building stock in Germany. Right now, all the vapor compression heat pumps are funded except domestic hot water heat pumps. And it plays an important role for the domestic market development. So the share of the funding of the overall market is relatively high. You will see on the next slide. I brought you here some information how the funding looks like. You have a website where you can apply for. It takes about 70 days until your eligibility is accepted. Another 130 days before the heat pump commissioning takes place. Another 100 days before the confirmation of the installation is finished by the installation company, and another 90 days up to what you get the payment. So this is just a median value of more than 100,000 of different funding applications. You can imagine that between eligibility and commissioning, a lot of the delivery times for heat pumps plays a large role, or the personal resources at the installation company, and this is the reason for the length of this time before everything is done up to the payment. Based on this process flow you have for the funding, you should have a look onto the market data I brought here with me. On the y-axis, you see the amount of heat pumps in 10,000s, and here on the development over several years. In blue, you see the application. That means that's the application date at which someone has started to use the portal for Get a Heat Pump Funded. Then you have in orange, you have the commissioning time, which is another date. It's the date of commissioning. In light blue, you have the heat pump funding, overall different funding programs in Germany. And in dark green, you have the heat pump market data from the German Heat Pump Association. So, and as you can see, the development is quite diverse. So it's not the same. Ideally, the funding should either be the same size of the market, which is not true, or the light blue color should be the same as the dark blue or the orange one, which is also not the same, where you can see that a lot of funding also takes place in some other funding programs and not only the one we have analyzed for the informatory node. So now we are going into this data of this BEG funding, in which the heat pump models are usually displayed and part of the funding applications. And this is our intersection and our chance to analyze the share of refrigerants of these heat pumps being funded as part of the German market. You see here now the same number of years from 2018 to 2023. And for each heat pump, you see the development over the years. It is more or less the same data as you have found it in the informatory node. You see in the application is actually the full colored bars, and the commissioning date is actually the data which is being shown as stripes here, so that you have the direct comparison to each other. And as you can see, the trend of propane, for example, is good visible. Also the trend for R32, there's an increase. One of the reasons of this is that in 2021, the funding also took into account air-to-air heat pumps, and a large share of these systems have R32. And then, of course, you still have a large share of R410A systems on the market. But as you see from 2023 onwards, the share of R407C systems is almost invisible. And in 2020, R454C systems came also onto the market. The others actually is quite interesting to see and to understand that the database we have analyzed for this presentation today also contains a lot of others, which is the combination of other refrigerants, but also the unknown, the systems charged with a refrigerant which was not identified actually. But as you can see, the database over the years becomes better and better. So that means, especially in the last years, I would say it's quite reliable what you see. And interesting to see here is that if you just have a look onto the data for the application dates, you see a certain increase. But if you look onto the commissioning time, you see that there's a relatively large fluctuations between R290 and R32 and R410A. So depending on the application and the commissioning date, sometimes people change over to other systems. But I would say the development of propane plus minus 3 to 4% is quite stable. The same kind of trend analysis we have done not only for all types of heat pumps, which was part of the informatory node. We also did the same for air-to-water heat pumps alone. So, and everyone should understand, if you have a look here, air-to-water heat pumps has a very large share on the heat pump market, and that means most of this, or almost everything of this development, at least for R290, is coming from the air-to-water market share and almost from no other heat pump type on the market. Here we see the same trend. It's quite a stable development, as you can see for R290 and R32. Again, you see fluctuations due to the different look either on the application date or the commissioning date. And this fluctuation is a bit larger for the R32 systems compared to R290. Yeah, so what can we conclude out of this? Looking onto the air-to-water heat pumps, which have already on the market a quite large share of offered heat pumps using R290, having a look onto these air-to-water heat pumps is important, and how the development could look like in future. It depends a lot on key markets where the gas to electricity price is high, but nevertheless, the development at least increased over the last several years. And here I brought just the data from Great Britain and from Germany, and as you can see, the increase for the German market is quite high. There was a drop due to this market development, as I think almost every one of you know or has followed in the press in the last years. And the same is for the Great Britain market, which was for me a quite positive surprise that this development also increased. So that means a lot of this air-to-water heat pumps as a share of these market data should be R290 systems. So what I would like to conclude with is that the real share of refrigerants, even just for Germany, might differ depending on the investigated databases. We got feedback from industry which says that the R290 share might be higher, as we have seen it here, due to the fact that we just see parts of the market by analyzing the BEG funding program data. We cannot say if this is true or not, but at least it looks quite promising. The referencing application date or the commissioning date leads to a lot of difference in the shares, which is very important to understand the properties of these different dates. The share of R290 systems and sales numbers is based on air-to-water heat pumps and domestic hot water heat pumps, but today we have not discussed the domestic hot water heat pumps, and it's also not part of the funding market. So for this reason, we are blind in terms of the development of refrigerants being used here. So, and the start of large growth of the heat pump market in 2022 with high shares of R290 was available, was possible, because some parties have forecasted that this development would also cause a limitation in growth. But I would say, just looking on the development as we've seen it, focusing more on R290 systems has not limited the market. I think these are other mechanisms we have seen in the drop of the market right now. Thank you a lot.
Thanks very much, Tor. Fantastic to have this insight into what's been happening in the market, looking back, and now we've got Born Palm, senior professor from KTH, who's going to look forward. And before we go to Born, please keep the questions coming into the chat. We've got about 10 minutes and then we'll open up for live questions as well. But please keep the questions coming into the chat. We'll try and answer them if we can. And it's great that other people are chipping in as well, really creating a fantastic sense of community. Anyway, over to you, Born, please.
Thank you, Graham. So the title of this part of the presentation is Future Outlook for the Hydrocarbon Adoption. And let me see here. I put three sentences here which say something about what I'm going to talk about. So propane heat pumps for outdoor placement are already on the market, and I'll show some of that. I will also say something about reduced charge, which is one way to keep safety with flammable refrigerants. And also, I will show you that the present heat pumps are not designed for minimum charge, so that there is a lot to do in this area, which I'll show you. But let me start going back to these slides which we saw before, and just want to point out that the heat pumps with the lowest specific charge are also the heat pumps with the highest COP. So there is no direct connection between low charge and COP. We can achieve very good COP even with a low charge. And we'll talk a little bit more about that. But let me show some examples of products which are on the market. EcoForest is one of the companies which have several models. And if we look at their smallest model, that is a 6 kilowatt unit. It is designed to be put inside. It is a water-to-water heat pump. It has a 150 gram charge of propane. And if you remember one of the slides of Daniel, you could see that if we have a charge of 150 gram of propane, then there are no restrictions on the size of the room where this heat pump should be placed. It's like a refrigerator. You don't have to consider where it should be put. So there is no, in this design, there is no ventilated enclosure, no propane sensor. There are two plate heat exchangers. There's no internal heat exchanger or desuperheater in this case. And of course, the COP of this system then is 4.3 at these conditions you see here. And of course, you could imagine that the COP could be slightly higher if we would allow ourselves to have an internal heat exchanger or a desuperheater, and also if we had a couple of more plates in the plate heat exchangers. But still, comparing the performance of this unit with those of with larger charge, the difference is very small. The same company also has units with larger capacity, up to 16 kilowatt. And in this case, the units have a tight ventilated enclosure, and it's designed so that you constantly have a slight under pressure inside this tight enclosure. The enclosure is connected to the ambient by two ducts, and you have a fan which can evacuate the enclosure rapidly in case of a leakage. So there is a sensor which stops the compressor in case of a leak, and also starts the fan with forced ventilation. So that is how the larger charges is handled according to this standard which Daniel told you about before, 60335-2-40. This was just from one company, but there are several other solutions also from other companies. This is from Swegon, another model also made for being placed inside. And here we have another one, master term. You can see the capacity here is 5 kilowatts, so the charge is less or equal to 150 grams. And here is another one, quantum, 6 kilowatt, 152 gram of charge of propane. So there are several such units on the market designed to be put inside. Of course, there are many more units or brands who have propane heat pumps for placing outside. And so what I want to show by this is that propane is not the future. It's already here. There are already units available on the market. I want to say something about research and what we can do. And this is just a small photo of one of the systems we have been working on at KTH. We have demonstrated with this unit that we can get 12 kilowatt out of 100 with a charge of only 120 gram of isobutane in this case. How did we reach this low charge? Well, one key issue is to not use the type of compressor which we usually use in heat pumps, but rather use a mobile air conditioning type compressor. I will show you the difference in a second. But the plate heat exchangers in this case were just commercial units, the most low volume ones we could find. And we also had in this case an internal heat exchanger, but we had to make that as a prototype. So that is one research project in this area. At Fraunhofer, they have a similar but much larger actually research project going on, or actually already finished, LC150. The goal here was to optimize heat pumps with the less than 150 gram of propane, and the solution with the low charge, which they demonstrated, was that they could get 12.8 kilowatts out of water-to-water heat pump with a charge of just 124 gram of propane. So about 10 gram per kilowatt. So more or less the same as we got at KTH. These were just examples, and there are many other labs in Europe working on hydrocarbons as refrigerant. These are some of the labs we're operating together with in France, Austria, Italy, Spain, Denmark, another lab in Germany. And as you can see, some of the topics, or one of the most common topics to work on, is charge reduction, but also design of the heat exchangers, hydrocarbon mixtures, life cycle, climate performance, etc. Yeah, so let's look a little bit on the components of a system and how we can alter them or change them to reduce the charge. So here we have an ordinary standard compressor. Weight is probably more than 20 kilograms, and the charge of oil is more than 1 liter. And the charge of propane in this compressor would be approximately 70 grams. This is the data based on tests we have made here in Sweden. But you could, of course, use some other type of compressor. And if we look to the left, this is a compressor of the type which is used in air conditioning systems in cars. And these are now being developed also for stationary applications. And you can see that in this case, it's less than 1 deciliter of oil instead of 1 liter. And the charge of refrigerant is 15 grams instead of 70 grams. And the weight is also a lot smaller. And just recently, there was a new type of oil-free turbo compressor presented onto the market. So there are developments ongoing now on components, specifically compressors, to which can be used in future systems to reduce charge. Sorry, I skipped one slide here. Another problem is, of course, the heat exchangers. And what can we do there? If you look to the left here, we have a plate heat exchanger with this was from about 15 or 20 years ago. And the charge of refrigerant with this type of plate would be about 0.9 liters per square meter of heat transfer surface. We made some prototypes already 15 years ago, which had 0.4 liters per square meter of heat exchange surface based on aluminum microchannel tubes. Now Danfoss has microplate heat exchangers which can give us about 0.5 liters per square meter, and the pressing depth is 1 millimeter in that case. And we also did some prototype heat exchangers with a pressing depth of less than 1 millimeter, and in that case we could get less than 0.4 liters of volume inside the heat exchanger per square meter of heat exchange surface. So there is a lot to do also with heat exchangers to decrease the charge. If we have a air to water heat pump, we need some air coils. And one of the problems with the air coils is the headers, which usually have quite a large share of the total charge, especially if we use microchannel aluminum tubes for the heat exchanger. But of course, there are ways to decrease the charge here also. And on this slide, you can see another type of header which could potentially be used to reduce the volume of the header and also the amount of charge in the header. So by this, I come to the conclusions, and of course, as Graham said, electrification of the heating sector requires rapid increase in heat pump sales. The F-gas regulation requires natural fluids in small systems in the future, not so distant future actually. And heat pumps with hydrocarbons are already on the market, so that is not really the future, but we can guess that, or we can expect that in the future we will have systems with smaller charge. So there will be less of a discussion about the risks connected to hydrocarbons if we can reduce the charge. So my projection would be that we can have cover most of the domestic market with, say, capacity up to 12 kilowatt with about 150 grams of refrigerant in the future. Thank you.
Fantastic. Thanks very much, Born. Amazing presentation. And just to hear that statistic, 10 grams per kilowatt of heat is fantastic. So that's really good news for us as practitioners. we've got about 10 minutes left, and we want to open the floor for questions. We've got a few questions in the chat, which we'll try and field as well. But if you want to ask a question, if you could put your hand up, okay, and we will ask you for your name and affiliation, and then to give your question. So I'm going to go first of all to Alok Kumar, if I pronounced you right. But if you could just give your name and affiliation and ask your question, that will be great, please, Alok. Can you hear me? Are you still with us, Alok? Okay, it's Kashif now. Okay, Kashif, over to you. Yep, go for it, Kashif, please.
Yep, can you hear me?
Yep, can hear you fine.
Yeah, this is Kashif Nawaz from Oak Ridge National Lab. A really interesting seminar, and I appreciate for condensing all the knowledge in for 1 hour. My question is regarding what is the general consensus for the minimum charge limit, maximum charge limit of 150 gram? Is it really well thought of? Any insight will be helpful.
Thanks, Kashif. Who would like to take that question? Daniel?
Yes, I can. I can try to answer. So, Kashif, you asked what is the rationale for it?
That's correct.
Well, it goes back in history. The charge. Okay, when people were starting to use hydrocarbons in domestic refrigerators, there was a preference to have some limit. So the standards that applied to domestic refrigerators, and which started to allow hydrocarbons, chose this 150 gram limit, and the rationale was a small European kitchen is about 8 square meters. So if you take 8 grams per square meter per cubic meter, which is the practical limit of propane, or 20% of the LFL, then it corresponds to about 150 grams. To be honest, I'd say that in practice, the logic went the other way. They said, well, we need up to about 150 grams in domestic fridges. Let's calculate back to find the size of the kitchen that would suit that. So that's the origin of it. And because there's now, I don't know, more than 1 billion domestic refrigerators with isobutane in, distributed around the world, and there's no there's no sort of trends of flammability risk, then that number has been assumed to be, let's say, safe or sufficiently low level of risk. And it's just stuck, to be honest, it's just stuck. And of course, when you consider whether risk is proportional to refrigerant charge, it isn't really. And of course, the more mitigation measures you apply to the system, the lower the risk becomes anyway. So, but it's just something that's stuck.
Fantastic. Thanks very much, Daniel. I'm going to move on. Van Baxter has put, I can't remember your first name, so you put a question in the chat. Do you want to just come online and just give that, please? Okay, well, the question is, what's the prospect for using hydrocarbons in larger commercial refrigeration and air conditioning systems? Is there an upper limit, 1 kilowatt or even 1,000 kilowatts? So would someone like to come in on that?
I can answer. Oh, okay, go on, Bjorn.
Yeah, please.
Well, I could just say that there are such systems and has been such systems installed in Sweden since, I think 20 years about. And of course, in this case, you don't have a direct, you have an indirect system. So you distribute the cooling with a secondary fluid. So you have a machine room with the hydrocarbon and then the secondary loop. And that has been working quite well.
Yes, I remember Daniel's dad in Wicker Refrigeration was involved in this in Sweden. There's a really big question in the chat from Daryl about skills. And is this a big question for us? Do we have, clearly we've got a trained workforce that's predominantly focused on hydrofluorocarbons, but is there a bit of a barrier here in terms of skills? And I wondered who might want to pick that one up. I don't know, Tor, if you fancy picking that one up, or
Can you repeat the question, please? Sorry.
Yes, it's a question about skills. Do we have sufficient trained workforce to be able to support the uptake needed?
Yeah, this is a very good question. Have a look into the chat, because I'm also not very experienced in this, but Monique has answered about data which are available for F-gas certified personnel, which is also able to handle small hydrocarbon equipment. So at least the number is larger than I thought. She writes that's about 29% of personnel which has got this training, and this amount will increase, I think, drastically in the next 3 to 5 years, because this is also part of the training, at least in Germany, that people get this training paid, or the companies get it paid better, so that they can afford to do this with their personnel.
Fantastic, thank you. And I'm looking at down the list, and we've got Jan Erik. Would you like to come in, please?
Wait, can you hear me? Yeah. I would like to say that in Gothenburg, they are planning, or they have already decided to install a 50 megawatt heat pump using R600A for sewage water to district heating. So large units exists. Thank you.
Thanks, Jan Erik. That's
just to
really...
comment on that. I think there are many industrial units which are of very large size. Also, for example, in Norway, for example. So this is, I mean, there's a difference between the commercial units where you have customers close by and industrial units. And I would say that the industrial units is a lot less of a problem than the commercial units.
Thanks, Spawn, for clarifying. We're going to go to Alexander Korpachai. I think you've got a question. Would you like to come in? Okay. Can we go to Solomzi? Apologies for pronunciation.
All right, no problem. Solomzi here from Tshwane University of Technology in South Africa. And one of the presentations you mentioned that there is no clear evidence of the relationship between the refrigerant charge and the COP, or the performance of the system. So I just wanted to find out, is it the case of the propane applied in heat pumps, or what is the case? Because I think, according to the research that I've done, I've seen the performance of the system maybe using R134A influenced by the quantity of refrigerant charge into the system. Could you please give some clarity on that?
Thanks very much. Anyone?
I guess that was a question to me. So, of course, if you add more surface area to the heat exchangers, you can definitely increase the performance. And also, if you add an extra heat exchanger, a desuperheater, for example, then you can also increase the performance. But what I wanted to say was that it is possible to design very good systems with high COP, also with a very low charge. So if you look at the plate heat exchanger, for example, it is possible to reduce the pressing depth of the plates, thereby creating more narrow channels, but the same surface area. So you can maintain the heat transfer surface area and still get the lower charge. So we have to think about how to develop the components to reach low charge, of course, with maintained capacity and maintained performance of the systems.
Thanks very much.
All right.
That's great.
Thank you so much.
Thanks.
Thank you.
Thanks very much. I think we're going to need to stop there and close there. And I just wanted just to wrap up, if I may. Thanks very much for all of the enthusiastic questions. This is the first webinar that we've had. We had 243 people on the call, and I worked out it's from at least 4 continents, maybe 5. I'm sure it probably is 5, so that's great. It's been absolutely fantastic. We need to thank our speakers, Emilio, Daniel, Thor and Born. We also need to thank our colleagues that have done all the work in the background on this, and I've got a big list of people that have been involved. I've got Monique, Nowen, Cindy, Maud, Natalie, Suha, and of course Jos is on the call as well, and she does a lot of work in the background on this. So brilliant from the IIR, fantastic event. If anybody's interested in finding out more about Commission E2, then please feel free to contact the IIR or contact myself, and we will put you in more contact. And if anybody is interested in a specific topic as a webinar, again, please contact the IIR and we'll try to see what we can do. Anyway, I'm going to close there. Thanks very much for everyone's input. Great event. Well done.